how are displacement, acceleration, and velocity related? Okay, we're not just going to look at this from a physics 1 standpoint. We're now going to start looking at it from a physics, calculus-based physics standpoint. Motion. So the first thing we need to talk about is motion. Motion is talking about a change in position. So when we refer to something in motion, we are actually talking about a change in position. If it's not in motion, there is not a change in position. And I am recording these, so. When we talk about kinematics, which is this first chapter, if you realize, remember what it says? Kinematics. There's a difference between kinematics and dynamics. When we talk about kinematics here, we are talking about the big difference is without regard to force. And those of you who took Physics 1 last year, you know that when we started talking about forces, we started talking about dynamics, and Newton is really dynamics, isn't it? So kinematics, we're not talking about forces here. We're really just talking about displacement, acceleration, and velocity and how those are related. Now, when we talk about acceleration, typically before we had derivatives and stuff, we talked about a constant acceleration or a zero acceleration. Now that we have derivatives, the potential for derivatives, we can kind of go past that a little bit. We don't necessarily have to have a constant acceleration. All right, so the other big thing is the difference when we talk about displacement, acceleration, and velocity is we've got to talk about scalar versus vector. You have to understand the difference between a scalar and a vector in this class, big time. All right, so under scalars, we're talking about distance. Its vector would be displacement. We're talking about speed versus velocity. Okay? We're talking about force. Force is a vector, but not in this one, and acceleration. Notice that acceleration does not have a scalar quantity that goes with it. So when we talk about scalars, we're really just talking about speed and distance. Now, the big thing you need to understand is the difference between speed and distance. Between distance and displacement and between speed and velocity. When we talk about a vector, we have to talk about a direction and magnitude. Y'all know this. A lot of this is going to seem the same. With the scalar, we're just talking about magnitude. What that means is that these are always going to be positive, and these could be positive or negative depending on their direction. Okay? So a scalar is just a magnitude, is the absolute value of whatever the vector quantity is. So, take a look at this first example here. We talk about Goku. We can see this guy right here. Goku starts at A. He goes and from point A to point C, and then he goes to point B. All right? His distance. What is his distance? If he goes from point A to C and then to B, how far has he gone all total?
16. 0 to 10.
From 10 back to 6.
Oh, distance. Oh.
From 0 to 10 is 10.
6.
And then this from 10 to 6 is 4.
6.
So he's gone a distance of 14.
Oh, I forgot my math.
Yes. I was trying to give you time to recover. Since he traveled 10 in the positive direction, but then he traveled 4 in the negative direction, that makes his displacement different. His displacement is 6. The difference between distance and displacement is only from the beginning point to the end point. In other words, displacement, which we call delta x, is your final position minus your initial position. So he started at 0, he ended up at 6. This is displacement. However, the entire route added up would be his distance he traveled. So oftentimes they're different. It's also the difference between taking an average and taking an instantaneous. Okay, so let's talk about average and instantaneous velocity. All right, so we know the speed is the rate at which an object covers a distance, okay? And velocity, so speed is what? Distance over time. But velocity is displacement over time. And those can be very different things. Okay? So you got to be careful. An average velocity versus an instantaneous velocity. An average velocity simply takes the beginning and the ending times in between two times, and you find the slope of the line connecting them. So for an average velocity, we would take from the beginning point t1 to t2, and we would find the slope. So the speed here, or average velocity, and we call this v average, we put a line over it, v average, okay? Or you could say v, and you could do average here, is going to be what? Slope of the line connecting those two, which would be x sub 2 minus x sub 1 divided by t sub 2 minus t sub 1, right? That would be the slope of those points. Think about it. This is the point x sub 1, t sub 1. And this is the point x sub 2, t sub 2, isn't it? Now, instantaneous velocity, however, involves a limit. Instantaneous velocity says, okay, so as we get closer and closer, as our time increment gets smaller and smaller, in other words, these two shrink up. As these two times get closer and closer and closer together, what value are we actually approaching right there for the slope of the line? Not necessarily 0. It's a limit, though, isn't it?
Yes.
Isn't that what it means? If we're going this way, where are we approaching this way? We're looking at a limit. You know that from pre-calc. So this is actually v, the vector v, which is different because it has a vector notation over the top of it. Vector v is going to be the limit of the change in x over the change in t as t approaches 0. So as it gets smaller and smaller and smaller, now, instead of delta x over delta t, because we're doing this, this really represents a derivative, doesn't it? The limit as it gets smaller. So we call this dx dt. So an instantaneous velocity is a derivative. Okay? Whereas otherwise we're dealing with an average velocity. Okay? So if we know the position, we can find it.
Okay.
So in physics C, speed can mean two very different things. We got average speed, which is what? Distance over time. Or we take the magnitude of the average velocity vector whereas instantaneous speed is the x dt, which is the magnitude of the instantaneous velocity vector. So we call it this speed, okay? Now, why did I put those around it? Because I'm saying that it's speed, so it's got to be positive, doesn't it? Positive derivative. All right? So, rules. These are important. Important rules for positive versus time graph. Boy, that was goofy. Position versus time graphs. Excuse me. Position versus time graphs. Positive. Ooh. I was tired. All right, so what do we know about a position time graph? If we have, guys, think about it. If we have a position time graph, we have x on this and t on this. What would the slope of that be? X over t. Change in x over change in t, wouldn't it? So if you had something happening here, The slope going this way would be, this would be delta x and this would be delta t. So the slope of the graph represents velocity. Okay? If it is a straight line, it is a constant velocity. Like this has a constant velocity because it has the same slope everywhere, doesn't it?
Yes.
If it's a horizontal line, in other words, if it looks like this, if x is here and t is here, but the graph looks like this, what is that telling me about the position? It's not changing, is it? It's not moving. So a horizontal line means the object is at rest. What does a parabola mean? Think about that graph.
Speeding up.
Or slowing down. But a parabola means constant acceleration, though. I want you to think about why that is. If we have a graph, let's say we have this. This is my position time graph. If we take our velocity time graph, what's happening here? Think about instantaneous. What's the slope of the line at the top?
It's 0.
0. So we know it's crossing this line somewhere, don't we? At 0, at that particular time.
It's the
So-
the triangle looking.
It's got a pretty steep slope, doesn't it? So it's starting with a positive slope. So it's starting somewhere up here.
And then it goes.
And then it's getting, now it's decreasing, isn't it? Until it gets to 0. So it's doing this.
It's this guy.
Yeah, no. Be careful.
Well, because you're starting off positive slope.
And now it's starting shallow and it's getting steeper, isn't it? But it's got a negative slope. So this one's going this way.
Oh.
Now.
Below the graph. That's right.
Yep. So now if you take acceleration, though, look what we have. This is now a constant straight diagonal line, isn't it? So if it's a diagonal line, what's the slope of that diagonal line going to be? A horizontal line again, isn't it? So that's going to give you an acceleration that is constant. So you can see how a constant acceleration will give you a changing velocity, which gives you a changing position, doesn't it?
Right.
Okay. That would be like a soccer ball being kicked or being dropped. All right, so what do we know? When the graph crosses the x-axis, the object is at the origin.
It's like the second.
Yes. A position graph, guys, a position time graph does not necessarily show you the shape of the object's trajectory. It just tells you it's going what? In a positive direction or a negative direction, doesn't it? All right, so let's talk about this. So, one quick thing about acceleration. If it is concave up, smiley face, right? Acceleration is positive.
It's facing down.
If it's concave down, acceleration must be negative. Frowny face is negative acceleration. This is for a position graph. Okay? So now let's look at a position time graph shown below. At which points is its velocity constant? This is a position time graph. So we are looking for places where the slope, right? Because the velocity now, and we've got a position time graph, so we automatically ought to think velocity, we ought to think slope, shouldn't we? At what point is the velocity or the slope of this graph constant? It's going to be anywhere where we've got a what? Straight line of any kind, don't we? B. Where else? D. How about E? Where is it 0 though? Just at B. It's got to be flat for it to have a 0 slope, doesn't it?
Yes.
Okay. So now, what about where is it negative?
D.
D. Where is the slope undefined?
Slope undefined is
A.
Where you can't tell. No, I can tell what the slope is there.
Is
I can tell what the slope is at B.
C.
Yeah. Why would C be undefined?
Since it's between B and
It's made a sharp turn, hasn't it, of some sort of sharp change? So how can you tell what it is right there? You can't. So it's C. It is undefined. Now it says at which point or points is the speed decreasing?
A, D. A is going.
I both think it goes down.
You're right.
Yeah.
It's starting here, and it's going here, and then it's going to 0, isn't it?
Yes.
So it is decreasing at A, because the slope is getting, the consecutive slopes of those tangent lines are getting closer and closer to flat or 0, aren't they?
Right.
Okay. Questions on how to read a position time graph.
Wait, what about D?
What about B?
I mean D.
Still going
D?
the same speed.
It's going the same speed. It says decrease.
D, the speed is not decreasing.
Speed decreasing. Okay, my bad.
Yeah.
Yeah. B's, I mean D's.
It's negative.
Yeah, it's negative. No, it's decreasing.
It's constant because it's a straight diagonal line, isn't it? It's constant. All right, let's calculate average and instantaneous velocity. Average velocity, or I'm sorry, average acceleration. Why does this say velocity then? I gotta go back and fix some things. So we know acceleration is look, if velocity is the rate of change of position, then velocity's got to be the rate of change, or acceleration has got to be the rate of change of velocity. Yes. All right. So average acceleration. If average velocity was the change in position over change in time, then what is the average acceleration?
Position.
Change in velocity over change in time. But instantaneous would be what? Yes, it would be the limit as t approaches 0 of delta v over delta t. So it is dv dt. Also, however, known as, and here's where you get into your lovely derivatives, we know A is dv dt, right? However, what we do know is what velocity is. That is dx dt, isn't it? So it is the now you see why it's written that way.
So you take the derivative.
It is the second derivative. Yes, you take the derivative.
First derivative and take that derivative.
Yes, if you have position, it is either the first derivative of velocity or the second derivative of position. The first derivative gives you, from position, the first derivative gives you the velocity, and then from the velocity you have to take the derivative again to get the acceleration.
So what is it? dt squared.
Well, it's just how it's written here.
Okay.
D squared x dt whole thing squared, right? It's just a formality of how it's written. It's not d squared t squared, it's just dt squared. So it is the second derivative of position or the first derivative of velocity. Okay? So let's talk a little bit about rules for velocity time graphs. We talked about them for position time graphs, so now we got to talk about them for velocity time graphs. And what is the relationship between velocity and acceleration? Are we good? Okay. Making sure. Okay. Important rules for velocity versus time graph. I complained about my TV today. I told y'all it wasn't a 75. They were supposed to be 75-inch TVs.
How much? What was
It's
it?
55. I said, Do you know how hard it is for kids to see off of a 55? How hard it is to teach off of a 55? No, there's 75-inch TVs in there. But there are pipes that run through these walls because of the plumbing, so they cannot put a big enough mount to put the 75-inch TV up, apparently.
Really?
I think it's crap, but they say you can't do it. So,
That's a nice little cover up, but okay.
yeah.
Put a cart.
I would take a cart over. I said, can I have my projector back? Because at least it's wider and bigger. This is less than half of what the projector was. It sucks. I still have to figure out how to get it to be the whole screen. I can't figure out how to get it to be the whole screen. It would be better at least if it was that wide. All right. So, rules for velocity versus time graphs. What does the slope of the graph represent? Acceleration. The area under the graph, however, go the other direction. The area under the graph represents what?
Displacement.
Has to be displacement. If the area is above the x-axis, it is positive. If it is below the x-axis, it is negative displacement, right? So you have to pay attention to that. All right. A line means what? If you have a line like this, constant acceleration. But a horizontal line on the velocity time graph means what? No acceleration. Zero acceleration.
Good afternoon, Austin High School. We had another great day. First, I'd like to wish congratulations to our debut football team as they beat Marshall last night. Great job by the debut football team. We also have some volleyball.
Somebody did at least.
Okay, good luck to our JV and varsity volleyball team as they play at Madison Academy against Madison Academy and New Hope. Good luck volleyball. Again, we had a great day. Students, please.
Oh yeah, they cost a
Also,
fortune.
we will begin selling student tickets in the cafeteria tomorrow. We'll be here again at $6 in the cafeteria. Be right here tomorrow. Have a good day.
That's the 325 bill. All right. So when the graph of a velocity time graph, crosses the x-axis. Let me finish real quick and I'll let you go change. When the graph crosses the x-axis, what's the velocity? The velocity is 0, isn't it? Which means it's changing what?
Direction.
Yes. So it's switching directions, isn't it? Now, here's a big thing. If velocity and acceleration have the same sign, the object's motion is what? Speeding up. Think about it. The acceleration is the push, isn't it?
Yeah.
So if you're going to the right and I'm pushing you to the right, you are speeding up.
Yeah.
But if that would be acceleration positive, velocity positive, right? So this is speeding up. In the positive direction. If the acceleration is negative and the velocity is also negative, it's what?
Speeding up in the negative
Speeding up in negative
direction.
direction. If the acceleration is positive but the velocity is negative,
Slowing down.
in which direction?
Negative.
Yep. Slowing in negative direction. What if the velocity is positive but the acceleration is negative? In the positive direction. Boom. We will pick up here next time, finish up. You do not have any homework tonight, but I suggest you use this time to go ahead and get your lab done. All right, we will pick up with this next time, and we will finish up